Welcome back, students. In this video segment, we will talk about one section, section 5.1, polar coordinates. In this section, we touch upon something that happens fairly frequently in mathematics for the sciences. First of all, we do a lot of graphing in calculus and physics and math for sciences, a whole lot of graphing. And a lot of that graphing takes place in rectangular coordinates in the xy plane. Very often we need to look at different coordinate systems for convenience for graphing points and curves and so forth. So today we're going to look at one of those alternate coordinate systems, and they're called polar coordinates. So before we do that, let's take a quick little review of what rectangular coordinates are. Okay, so what are rectangular coordinates? Rectangular coordinates are give a way to locate points in the xy plane. And how do we do that? Well, suppose we have a point that we want to locate in a flat plane. So what we would do is we would, see if I can do this. We would state an x value, an x coordinate, and we would move that distance, or not quite a distance. It's more of what's called a displacement in the x direction. And then we would move a corresponding displacement in the y direction. And we would state the location of the point as x comma y. Let me do this. I should have practiced this a little bit. X displacement, y displacement. Now we would state the resulting location or point as an ordered pair x comma y. And notice I changed my verbiage from distance, from an x distance to an x displacement. The thing is, the x and y coordinates don't have to be positive, they could be negative. And distance is always positive, so to fix that semantically, we refer to x and y as displacements. To get around even using the word displacement, we just say that their coordinates where x and y could be positive, negative, or zero. They could be any real numbers. Okay, so let's take a look at another coordinate system. Let's imagine we're in the sky looking down at an airport. So we're really high in the sky, above the altitude of that airplanes fly, and we're looking down from the sky. And let's say that this fat black dot here is an air traffic control tower. Okay, and what an air traffic control tower essentially does is it sends out a radar signal. Radar signal travels in a straight line, but the device turns also at a constant rate, so that radar signal goes around and around and around and around. So let me see if I can represent that. So the radar signal goes around and around. It keeps going around and around and around. Okay, so its new location at that angle might be, let's see if I can borrow my red arrow again. Might be about right there. Okay, so the radar signal is traveling round and round and round and round and round. So the red arrow is the location of the radar signal after it's gone one revolution in about I don't know, a little more than 3/4 of a revolution. So a little more than 1 3/4 revolutions. Okay, so how does this locate airplanes? Well, let's take a look. So off camera, I drew the control tower again, and there's the radar signal in its sort of initial position, and here's an airplane. Again, we're looking straight down from the sky. Okay, so the control tower sends out the signal, and what's going to happen is, let's see if I can do this. What's going to happen is the signal, when it's sent out, the signal will bounce off the airplane and reflect back to the control tower. Okay. At that moment, the control tower will measure this angle, sort of the angle of elevation, if you will. We used to call this the angle of elevation. We'll measure that angle, and we'll measure also the distance to the airplane. You see, the radar signal is traveling at very close to the speed of light, okay, which is well known. So the signal, when it bounces off the airplane, is received back at the control tower, and that the amount of time that it took for the signal to come back is cut in half, and that measures the amount of time it took for the signal to hit the airplane. And since rate times time equals distance, that amount of time that was measured multiplied by the speed of the radar signal, speed of light, gives you the distance, and we'll call that distance, let's say, r. Okay, so the control tower measured the angle, took note of the angle when the signal was received back at the control tower, and the distance is measured, and the coordinates of the airplane then are given by that displacement, and there I am calling that r a displacement instead of distance, and we'll come back to that in a while. That r, what you can think about right now, is a distance, and the angle theta. Okay, notice I'm not stating a horizontal displacement x and a vertical displacement y. I'm stating a distance from the control tower, which we could call the origin, or have it coincide with the origin, and the angle theta off this fixed line. So let's be more complete about this. These are called polar coordinates. Polar coordinates. Okay, and you can see why they'd be a little more convenient than rectangular coordinates, since the radar signal is sweeping out angles and measuring the distance from the control tower, the new origin, if you will. Let's call that fixed line, the polar axis. And that polar x-axis can coincide with the positive x-axis if we decide to do that. And very often we will. So we can call the polar axis a sort of renaming of the positive x-axis. The control tower, the actual name of that is not the control tower. For our situation it is. We call that the pole. The pole is very often where we would put the origin. So we have this ray, this half of a line, which we call the polar axis, and then this sort of new location for the origin, or new renaming of the origin, we call the pole. And we state the sort of, for now, the distance r and the angle theta to locate points in what's called the polar plane. Okay, so the polar plane it's the same as the xy plane, where we're using polar coordinates to locate points. Okay, so in practice, very often we place or imagine the polar plane being right on top of the xy plane, so we can also look at x and y in the same diagram. Okay, so let's practice with this. I've done a lot of talking about definitions. Let's practice. So, for example, let's sketch. Let's sketch in the polar plane. Part A, let's say 2, pi over 4. Okay, so when we state points in polar coordinates, we have to remember that we're not looking at x and y. We're looking at r and theta. So this little 2 here, that's a displacement from the origin, or from the pole. And this pi over 4, that's an angle off the polar axis, or the positive x-axis. Okay, so let's do this. Now, when I plot polar points in the polar plane, I do things a little differently than your textbook might. The idea is equivalent. The only difference that I do is that when I graph the sort of the red line that went from the control tower to the airplane, I graphed the entire x-axis, including the negative x-axis, rotated through that angle, and I'm hoping that'll make sense in a few minutes. Let's start this over again. Let's plot this point in the polar plane. So what I'm going to do is I'm going to draw the xy plane. I'd like to draw it in black. So let's start over again. I'm going to draw the xy plane. I'm going to imagine the polar plane placed right on top of it. So the positive x-axis is the polar axis, and the pole is at the origin. Okay. Now, when I plot points myself, I like to plot the angle theta, or consider the angle theta first. Okay, so I would rotate a copy of the x-axis, the entire x-axis, not just the positive x-axis, but the entire x-axis through an angle of pi over 4. So let me see if I can do that. So here is the entire x-axis rotated through an angle of pi over 4. I'm going to hope I can do this. Let's see. I think I'll do it in red. All right. I can always redo it, I guess, if it doesn't work. So here's the entire x-axis rotated. This turned out pretty well. Rotated through an angle of pi over 4. So there's our angle pi over 4. Pi over 4. And then if I were on the unrotated x-axis, this might be x equals 1. This might be x equals 2. Let me move my angle over a little bit. Here's the angle of pi over 4. So on my rotated x-axis, here's 1, and here's 2. So I move 2 units, positive 2 units, along that rotated x-axis right here. I'll give it a nice thick point in, let's say, green. Right here. And that's the point 2, pi over 4. So when you're graphing in rectangular form, you might look at the x-coordinate first and the y-coordinate second. I prefer to look at the angle first, and then along that rotated x-axis, then I plot the point. Okay. So let's plot another point just to get familiar with this stuff. So let's say B. Let's plot the point 4 and 11 pi over 6. Okay, once again, let's draw our x-axis. Okay, and then I'm gonna consider the angle first. Okay, so I'm going to rotate the entire x-axis. Your author just rotates the pole, the polar axis, but I choose to rotate the entire x-axis. Again, the reason for that's going to come up real soon. Okay, so I'm going to rotate the entire x-axis through an angle of 11 pi over 6. 11 pi over 6 is in quadrant 4. It's an old friend of ours, that angle. And there it is. Then along that rotated x-axis. Now, you got to keep track of where the positive x-axis got rotated to. That's something I didn't measure or mention. So if the x-axis used to be here, okay, if the x-axis used to be here and I rotate it through an angle of 11 pi over 6, then the positive x-axis is going to be now pushing into quadrant 4. Okay, so these are the positive x-axis. In fact, I might even do this. Let's say the positive x-axis is now in quadrant 4. Okay, so if I want to plot the point 4 rather, and 11 pi over 6, what I might imagine doing is along the unrotated x-axis, here's 1, 2, 3, 4. Then along the rotated x-axis, I would go 1, don't have to draw these in every time. 2, 3. You don't have to draw these little dotted angles in. 4. I'm just trying to illustrate to you that I've rotated the x-axis, through an angle of 11 pi over 6, and I've kept track 1, 2, 3, 4, 1, 2, 3, 4 of where the values on the x-axis, rotated x-axis, ended up, and that's my point. So you might be thinking, why do you do that? We don't need the negative x-axis, so why would you rotate the entire x-axis? It's coming up. It's coming up real soon. Okay, 11 pi over 6. All right. So our task now is to develop the concept of polar coordinates further and to address 3 common problems that students have with polar coordinates. 3 very, very common problems. Okay, so let's take a look at each of those problems as we learn and develop the concept of polar coordinates further. The first of the 3 major problems, 3 common, let's say, common problems that students have with polar coordinates. The first is, it's going to sound funny at first, but we'll look at it carefully. Multiple representations of points. What in the world does that mean? Well, in rectangular coordinates, we don't have multiple representations of a single point. What am I talking about? Okay, I'll show you what I'm talking about. Let's see, here's the rectangular, the first quadrant of the rectangular plane. And suppose I wanted to plot the point, let's say 2, let's do a little better. Let's do 3, 1. We would look at the x-coordinate, move 3 units along the x-axis, we'd move 1 unit along the y-axis, and we would plot our point. 3, 1. There is only one representation of that point. There's only one way to designate that thick point that I'm putting there, and that's by writing 3, 1. You can't reverse the coordinates, you get an entirely different point. You can't change the values 3 and 1 and get the same point. You change the point if you change the numbers of the coordinates. In polar form, this is not the case. In polar form, this is not the case. Let's consider again in polar form. Consider the point. Let's see, what was the first point? Was it 2 or 3? It was 2 in pi over 4. Let's consider the point 2 in pi over 4. One more time. So here off camera, I copied and pasted our original point. 2 in pi over 4. Rotate the x-axis through an angle of pi over 4. And move along that rotated x-axis 2 units, and we get 2 pi over 4. Okay, now what happens if I keep 2, but I continue to rotate the x-axis through another 2 pi? In other words, I have 2, and then pi over 4 plus 2 pi. Okay, what is the angle going to look like? It's going to look like, here I'm going to draw it in a new color here so I keep track of the angles. Let's say, I guess red. So here's pi over 4 plus 2 pi. Okay, well, if I move 2 units along that rotated x-axis, I get to the same point. Okay, now what happens if I take and add another 2 pi to that? I have pi over 4 plus 4 pi. If I add another revolution, I'm going to get the same point if I take and use the same r value. What if I take my original angle 2 and pi over 4, and from pi over 4 I subtract 1 revolution. I rotate the negative x-axis. I rotate the x-axis in the negative direction from pi over 4, a full 2 pi. I'm going to get the same. I'm going to get the same location. I'll put that angle in green. Oh, that's the ugliest angle I've drawn today. That's not much better. So here's the angle pi over 4 minus 2 pi. Okay, or negative 7 pi over 4. That's the same location. These are the same points. These are all the same point. The original 2 and pi over 4, and all of these are the same point. Same location. Okay, so one point has many, many different representation. A single point in polar form has infinitely many representations. Infinitely many representations. Infinitely many. And you might be able to get an idea of why that's necessary in physics or in the sciences if you consider planetary motion. If you consider our planet moving around the sun. Our planet moves around the sun in an approximately circular orbit. It's really elliptical. And every year our planet sweeps out an angle of 2 pi. So if we don't consider that the universe is actually expanding and that our solar system is moving, if we just consider our location around the sun, moving around the sun as the trajectory of a planet in the plane, every year we sweep out an additional angle of 2 pi and end up in the same location that we were a year ago. Okay, so in the sciences, in particular in astronomy, it's critical that we have multiple representations for the same point. And this can take place on a much smaller scale. In chemistry, you have particles orbiting other particles, electrons and protons and so forth, twirling round and round and round each other. Well, I guess not around each other. I guess the proton moves around. Wait, I don't remember my chemistry. I think the electrons are the things that are swirling around. So in any case, the orbit of electrons are also periodic. Periodically, they occupy the same location in space. So this idea of having multiple representations of points is critical in the sciences. So in fact, the ordered pair 2, pi over 4 plus 2k pi are all, I have to be careful how I say this, are representations of the point 2 and pi over 4. Okay, so this is one of the first problems that's one of the three big problems that students have with polar coordinates to begin with. It's kind of unsettling. You think you might have one point gets one representation, but no, we have infinitely many. And here's the thing: these representations 2, pi over 4 plus 2k pi. These aren't all the representations of that single point. There's another way to designate these points. There's still another there's still another formula, if you will, for the same point. Okay, and that brings us to our second main problem. The first problem is that there are multiple representations of a single point. The second problem is that R can be negative. The first time we saw R was back in section 2.4. Okay, we had locations of a point A, B in the rectangular plane, and we had the distance from the origin, and not a displacement, an actual distance from the origin. We used r for that, and we made r positive. And we had cosine of theta equals a over r, sine of theta is b over r, etc., etc., etc. Well, now we're allowing r to be negative. Okay, and this is going to explain why when I plot points in the polar plane, I choose to rotate not just the pole, not just the polar axis, but the entire x-axis. And let me explain further. Okay, so example, plot the point, let's say -2 and pi over 4. Okay, so we'll start this exactly the same way as we did before. Here's the x-axis, or not the x-axis, xy plane. And now let's draw a copy of the x-axis. Let's rotate that through, oops. Let's imagine rotating that through an angle of pi over 4. So here's the entire x-axis rotated through the angle pi over 4. So here's the x-axis, just a copy of the x-axis. We're not rotating the whole plane, we're just rotating a copy of the axis. So here's x equals 1, here's x equals 2, here's x equals -1, here's x equals -2. So I'm going to rotate those values as well. So here's on the rotated x-axis, x equals 1, x equals 2, x equals -1 on the rotated x-axis, -2, and I'll put kind of in quotations here x, because it's really not the x-axis. The x-axis never moved. And I'm rotating the polar axis, the extended polar axis, if you will, through the angle of pi over 4. So there's pi over 4, the angle. Call the angle in red here. And then we move not +2 along that rotated x-axis, we move -2. So the point -2 comma pi over 4 is in quadrant 3. Okay, and this is a little unsettling for students because we're not used to having r negative. Well, it's just fine. There's nothing wrong with r being negative. Okay, I should have said in my example in the polar plane, because if I just say plot that point, you have to kind of ask in the context of this section, well, is it the rectangular plane or polar plane? You can have x values being pi over 4, y values being pi over 4, and so forth. So I'll be more careful with that. So let's do another one. Plot another point with negative values for r. Let's say, let's plot the point -3 and 5 pi over 6. Okay. Once you get used to the idea that you could have multiple representations of points and that r can be negative, it's not that big of a deal. It doesn't have a real long learning curve. It doesn't take a long time to get used to this. It just takes a little practice. So let's imagine then rotating the x-axis through an angle of 5 pi over 6. So 5 pi over 6 is in quadrant 2 in standard position. Okay, so there's our angle 5 pi over 6. Okay, so here's the original positive x-axis. Here's x equals 1, x equals 2, x equals 3. So along the positive values got rotated. The positive x-axis is now pushing through quadrant 2. So here's where the positive x-axis is now pointing, positive x, and here's +1, +2, +3. I literally just move the x-axis, rotate it through an angle of 5 pi over 6. So here's 1, 2, 3. Here's 1, 2, 3. And I'm not interested in 1, 2, and 3. I'm interested in -1, -2, and -3. -1, -2, -3. And that puts my point in quadrant 4. Okay. Okay, so let's practice with pulling both of these ideas, multiple representations and negative coordinates. Find all possible representations of the point 2, pi over 4. The first point. Okay. So here's our original drawing again, and we determined before that 2 and then pi over 4 plus 2k pi, that gets us to the same place over and over and over and over and over again, where the positive x-axis or the entire x-axis just keeps twirling around a full revolution from pi over 4, either in the positive or negative directions, and we still end up with the same location, moving 2 units along the rotated x-axis. Now, I would like to have a representation of that same point using negative values for r, or a negative value for r. So here's what I mean. I redrew, well, I cut and paste. I cut and paste the same point, same old point as before. Almost lost our x-axis there. But I got rid of the angle. So if I want this same point to be represented with a negative value for r, what's that r value going to have to be? What's that r? Well, before it was 1. You had to move 2 units from the origin in the positive direction. You got 1, 2. Well, now I want that to be -2. I want the r value to be -2. So what theta value is going to be required to push the x-axis, the positive x-axis, through quadrant 3 now? Okay, I'm going to need to take pi over 4 and add another, and continue to push the axis another pi. If I take the angle of pi over 4 and push the x-axis another pi, not 2 pi, just 1 pi, then the positive values will be now pointing through the third quadrant. So here's x equals 1, here's x equals 2. Okay, that means -1 and -2 are x values on the rotated x-axis in quadrant 1. So the smallest angle that I can do that, or get a point, I'm sorry, let me start that over again. The smallest angle then that I can rotate the x-axis through so that I get negative x values pointing in through quadrant 1 would be 5 pi over 4. So this point, -2, 5 pi over 4, is the same location. It's the same, represents the same point in quadrant 1 that I had before with 2 and positive pi over. The same point. But the r values are negative. Okay. So is it enough to say that all representations of the point 2 pi over 4 are given by 2, and then pi over 4, and then add a full revolution as many times as you want, and also -2 and 5 pi over 4. Is that it? Any other ones? Yes. I could continue turning or rotating the rotated x-axis that corresponds to negative values. Negative 2 is the x value in quadrant 1. I can continue to rotate those by full revolutions in either the positive or negative direction. So all representations of that single point are either represented by 2 and then pi over 4 plus 2k pi in polar form, or for negative r values, negative 2 and 5 pi over 4 plus 2k pi. The same point has infinitely many representations. Okay. If this seems a little overwhelming, I really want to assure you that my students tend to experience this little bit of overwhelming feeling at first, but it goes away quickly. You just have to practice with homework problems, and things get not so bad. Okay, I say not so bad, and they become not a problem at all, because it is a little more difficult to consider points in polar form. We got multiple representations. We got negative values for r, but you get used to it. Okay, so let's head toward the third problem that students have with polar coordinates when just learning polar coordinates. In order to get there, we need to talk about something very important, a very important aspect of having more than one coordinate system. Very often in the sciences, we need to go back and forth between coordinate systems. We need to represent points specifically in rectangular form, and also convert them to polar form, and vice versa. We need to be given points in polar form and convert them to rectangular. The third difficulty is in one of those conversions, and I'll let you know when we get there. I think you'll understand. So let's talk about converting from polar to rectangular, and vice versa. Let's talk about first polar to rectangular form. That means if I give you a point x, or rather r comma theta, find the corresponding point x comma y. So let's do one for an example. So example, convert from polar to rectangular. Let's say a 2 comma pi over 4, the first point we started out with. Okay, well, let's approach this more generally first. What are the relationships between x and y and r and theta? If you missed what I just said, I'm gonna draw it now. So here's the xy plane and the polar plane placed right on top of each other, so that the pole is at the origin. And let's do this. Okay, that'll work. Ooh, that didn't work. Hold on here. Okay. Here is my point. My point is located. Oh, that didn't turn out real nice. Give me a second. I'm going to have to make a nice fat dot to make that point show up. Here's the point. And I'm going to put in the rectangular coordinates, x, y, and I'm going to also put in the polar coordinates, r and theta, so we can view all 4 coordinates on one drawing. I would like a relationship. I'd like a few relationships. I'd like a set of equations that'll allow me to transform or to convert from one system to another. I want to go from polar to rectangular. So if I want to go from polar to rectangular, that means I'm given an r and a theta. I need an x and a y. So I need a formula that's going to say x equals something and y equals something. I'm looking for rectangular. So what's the relationship? Let's just look at one coordinate at a time. What's the relationship between x and r and theta? Just x. Don't worry about y. Just x, r, and theta. Okay. Here's your hint. I'm drawing in the right angle. It's a little virtual triangle here. Okay, so remember, x over r, adjacent over hypotenuse, is cosine theta. I want x, so multiply both sides by r. X equals r cosine theta. Bingo. That is how we get x from r and theta. Similarly, y over r, opposite over hypotenuse, equals sine theta. So y equals r sine theta. These are the two equations that will allow you to convert from x and y to r and theta. X equals r cosine theta, y equals r sine theta. So if I'm looking specifically at the point 2 and pi over 4, where my r is 2 and my theta is pi over 4, that means x equals r2 cosine pi over 4, and y equals r sine pi over 4. And we know these values. These are very simple values for us at the end of our semester. Cosine pi over 4 is radical 2 over 2, so the x-coordinate is radical 2. The y-coordinate's the same. It happens to be, because sine and cosine of pi over 4 are both radical 2 over 2. So the answer is radical 2 and radical 2. The x and y values are both radical 2. It's very, very simple, the concept of converting from polar to rectangular. So, B. Let's say -3 5 pi over 6. Again, I want to go from polar, r, and theta to rectangular. Very easy. X equals r cosine theta. So r equals -3. So x equals -3 cosine 5 pi over 6. And y equals -3 times the sine of 5 pi over 6. All right, so let's keep going with this. These are old friends, if you will, these angles. You could use a unit circle or reference angles. The cosine 5 pi over 6 is in quadrant 2. In quadrant 2, the cosine is negative. Or directly off the unit circle, we get negative radical 3 over 2. -3 for the y value. The sine of 5 pi over 6. Sine is positive in quadrant 2. Reference angle is pi over 6, or directly off the unit circle. So we get 3 radical 3 over 2 and -3 halves. So the answer is x equals 3 radical 3 over 2 and y equals -3 halves. Okay, so that's not the third difficulty students have. The third problem that students have is finding theta when converting from rectangular, the other way around, rectangular to polar. And I don't think it's going to be too rough for you, because finding theta requires that we use some work that we did in chapter 3. And it wasn't that long ago that we studied chapter 3. Anyways, let's find equations that convert from rectangular to polar. So here is Here's our XY plane. Here's our point. See if I can draw this better this time. We'll see. I'm trying to draw our point here. Oops, I want a straight line. This one turned out a little better. Okay, so here's X and Y. Here's R, and here's theta. Okay, so if I want to convert to polar, that means I want to take X and Y and convert to R and theta. So I need equations. If I want R and theta, I need something that's going to say, well, R equals and theta equals. I don't quite get them. I don't quite get equations that will state explicitly R equals and theta equals. Okay, here's what I'm talking about. What's the relationship between R and X and Y? R, X and Y is just a Pythagorean theorem. R squared equals X squared plus Y squared. Here's what I mean. I don't get an equation that says R equals. I just have an equation that says R squared equals. So why don't I just take the square root of both sides and have a formula for R? Because R can possibly be negative. So depending on the context of the problem, you would solve for R squared and then either take the positive or negative square root. If you were looking for a negative value for R, you take the negative square root. Okay, that's not the hard part. The hard part is finding theta. Well, what's the relationship between X and Y and theta? X, Y, and theta. It is tangent of theta equals opposite Y over X, adjacent, opposite over adjacent. And this is the problem, going from tangent theta into theta. Because that means you have to solve a trig equation, and that requires the methods of chapter 3. Chapter 3. 3.7 and 3.8. 3.7. Okay. Let me be real explicit about this. Let's solve a problem. Let's convert. Let's say from, for example, rectangular to polar. Rectangular to polar. And the point is going to be -1 and radical 3. So we're in rectangular form. So this is X and this is Y. I want R and theta. I want R and theta. Okay. Okay, so the first thing I'm going to do, actually the first thing I want to do is I want to draw this point. Okay. We're gonna have a little rough spot here, so I want to draw the point. So here's the XY plane. Here's, if let's say this is -1, here's X and here's Y. And radical 3, that's about 1.7. So here's radical 3 up here. So here's our point. Right there. And I'm looking for R and theta. So let me do this. Let me draw, if I can, a rotated x-axis. I got lucky. I didn't get that lucky. All right, I wanted red anyway, so here. Whatever. Not whatever, I'm going to fix it for us. Okay. There we are. Let's see if I can do this. That's okay. That's not bad. Okay. Okay, so I'm interested in R. If I have the positive x-axis pushing through quadrant 2 for the easiest value for R would be positive, and I want theta. Let me put that in red. I want R and theta. I want to put them all in, all those polar coordinates in red. R theta. R theta. All right, let's do it. R is simple. R squared equals x squared plus y squared. It's very simple. R squared equals -1 squared plus radical 3 squared. So R squared equals 1 plus radical 3 squared is 3. So R squared equals 4. Now you could take the positive or negative square roots. Okay, but keep or be easy on yourself. Be gentle on yourself. Let's take and choose. Oops, not square root of 2. I guess we have to choose the right value. Let's choose the positive square root. So R equals 2. Okay, so that's fine. That's fine. It's theta. It's theta that gives us a little bit of a problem. So tangent of theta is the y coordinate, radical 3 over -1. Okay, or the tangent of theta equals negative radical 3. Your calculator won't help you with this. You might think, well, no, all I have to do is take the inverse tangent and I get value of theta. Yeah, you'll get a value of theta, but you'll get the wrong value of theta. You see, the calculator is programmed to give you inverse tangents between -π/2 and +π/2. The tangent, or the calculators are programmed to give you the values of the inverse tangent as negative values in quadrant 4, so between -π/2 and 0, or positive values in quadrant 1, so -π/2 to π/2. If you were to use your calculator, theta calculator, and you were to put it in, say, the degree mode, you would get -60 degrees. And that's wrong. That's wrong. Look where I have my theta pictured. Look at theta in red. Theta is in quadrant 2. -60 is in quadrant 4. And our point isn't in quadrant 4. Our point is in quadrant 2. So this is wrong. This is wrong. The calculator will not give you theta. So how are we going to find theta? For us, it's not so bad because we had section 3.7 not that long ago. We use a modified version of QRA. It might not be real pleasant for you to look at this now, but timing's good here. We have our final exam coming up real soon, so we're going to need to review this anyway. So we use a modified version of QRA. So let's solve this. Well, if we were using QRA, the quadrants where the tangent is negative, remember all students take calculus, the device for determining positive, quadrants where the trig functions are positive. The tangent is positive in 1 and 3. So the tangent is negative in 2 and 4. So what we would do back when we were solving trig equations, we would put 2 and 4. But we modify this method a little bit because we have to do kind of a reality check for our particular problem. We're not in quadrant 4. Where are we? We're only looking for the quadrant 2 answer. Look at where the red angle is. So the reference angle for tangent equals radical 3 is π/3. You can pick that right off the unit circle if you want. And then you write the answer. So if the reference angle is π/3, I'm going to put that reference angle right in here. The reference angle right here is π/3. What's our answer? The answer has to be pi minus π/3. Look at it. If π/3 makes up the distance from theta up to the negative x-axis, then the angle has to be pi, go all the way to pi, and then come back by that reference angle. And that's 2π/3. Okay, that means our answer is, what was our value for R2? 2 and 2π/3. Okay. And that is our introduction to polar coordinates. What I would do if I were you is, while this is fresh, I would go ahead and start some of the homework for section 5.1 and get through this little bit of a learning curve with the polar coordinates. I think that you'll be surprised with yourself. It won't take you that long, and you'll become pretty much experts at plotting polar coordinates. And that's it for this section. So I'm looking forward to talking with all of you again very, very soon.